Our project mentor from Y-Data is Yuli, and the partners we worked with at IMPERVA are Matan and Yuri. So IMPERVA is a cybersecurity company, and one of their main softwares protects websites by detecting dangerous scripts. So most websites on the client side are programmed in a language called JavaScript, and JavaScript can be sensitive to a phenomenon that's called obfuscation, which can show us that the script can be potentially dangerous. So what is JavaScript obfuscation? We will see the simplest code example ever in the world, right? Anyone who has ever looked at code knows the hello world function. And after we put this super simple little function into an obfuscation software, it looks like this. So now there's a whole lot added, a lot of noise. We don't understand anymore what this code is supposed to do. But the compiler, when it reads this code, actually still will execute the same simple hello world, just with a lot of unnecessary stuff happening around. Why do people use obfuscation tools? The reasons can be innocent or so-called white hat, which is to protect the copyright of the code, right? We don't want people to steal intellectual property of certain code. On the other hand, the black hat user could be somebody who actually writes a malicious script and is trying to hide the intention of the code. So our goal for the project, as a basic goal, was very simple: to build a binary classification tool that detects obfuscated scripts from one specific obfuscation tool versus regular clear scripts. The advanced goal, which was much more challenging, was again a binary classifier that detects obfuscators regardless of the tool that they came from. And the bonus goal was to test our model on some completely new and unseen obfuscators that were not part of our initial training data at all. We measured our results with an F1 score. So why is this a hard task? If we look at these two scripts, which of them do you think is obfuscated? Okay, it is the right one, okay? This one is clear text, even though we can see there are some patterns in there that don't look like the nice hello world function, which is one of the problems, that some of the clear texts also have some stuff in them that doesn't look very typical. On the other hand, this obfuscator, let's test. This obfuscator creates outputs that also are not as obvious as the first example that we saw. And this shows us that we can have a wide variety of outputs from different obfuscators. Basically, this is a problem of out-of-distribution generalization. And to illustrate this, let's imagine that we build a classifier that detects cows and camels, a vision model. And the pictures in our training set would be very typical: camels in the desert, cows with a green background. Once we test this model, maybe we would come across an image like that of a cow in the desert, and our model would make a mistake and classify this as a camel. Why? Because it learned to use the background instead of the main feature itself of the animal. So similarly, in our project, the goal is to try to get our model to learn the real core features of what makes an obfuscator in order to detect things in a robust and general way. The data we used contained about 190,000 samples, which were actually from an open source data set that IMPERVA made accessible to us, or helped us to get. We used about 170,000 of the samples for training, the rest for testing and validation. And additionally, for the bonus goal, we used about 10,000 other samples from 3 different unseen obfuscators that we only used at the very end of our project. The data was split to about 50% clear text, and the other 50% were obfuscated, and actually these obfuscated scripts came from some of the clear texts that were passed through these obfuscation tools. There were 4 different obfuscators, and here you can see an example of the same script after being passed through these 4 obfuscators. And again, we can see the variety. Even from a first glance, they're not very similar to each other.
Our basic goal, as you can see, we built 4 different experiments, 1 experiment per each obfuscator, while each experiment, a new model is trained. And we did, we took our samples of a certain obfuscator and just split it, as you all know, split of train and test, and by that we did the basic goal. For the advanced goal, in this way, we examine how well our models are generalized. To do so, the design of the advanced goal is as follows. Also, 4 experiments. However, in each train set, we held 3 different obfuscators, while in the test, we had the 4th one, which is unseen. So in that way, we can know how well our model is generalized. So how did we start our journey of researching for this project? So at the beginning, we decided that we want to go over a classical approach of developing our own features, like by handcrafting features, feature engineering, and using some classical machine learning models. And as an input, we use first the raw scripts, the raw JavaScripts, as we accept them from the dataset. However, we did some manipulation for them. One of them was removing all comments. And the other one is using the ASTs, which is the abstract syntax tree, which is a tree, let's say, a graph of the program, of the JavaScript program, as the compilers see it. Okay, so it can give us much more, maybe, insights about the script themselves from that kind of view. So then we extracted several elements from these inputs, kind of, let's say, reserved words in JavaScript, ASCII characters, types of the ASTs, different elements from the code. And then once we got these counts of different things, we can produce also some patterns. So then we used some n-grams in different ways. While we have these counts and n-grams, we can produce probabilities. And once you have probabilities, you have distributions of things. However, because we wanted to generalize, to build features that are really strong in generalization and not depending on a single probability or count, we used 2 tools from information theory. The first one is entropy. Okay, so we take the sum of entropy of the entire distribution of a single sample, let's say, for example. And the other one is the KL divergence of the distribution from a reference distribution of a clear text that we made from beforehand. By that, we were able to compress the entire distribution of things into a single feature. Another important feature that we came up with is readability features, several readability features that depend on the simple fact that JavaScript, in certain way, it can be easily read as English words. So we just took some of the words, compared them to English dictionary, and gave a score. This is the readability. That's simple, but really effective. And the last one is the ASTs. ASTs, as I mentioned before, it's a graph eventually, and we used also some of the feature from them, such as depth and width of the graph. We end up with 13 different features, which we then utilize or model using our ML models. Okay, so at this point, we had some good, good results with the classical approach. However, we want to make it, from one hand, deeper and make the feature engineering even better. However, we want to test new ways, in new things, and new directions. And then we approach to the deep learning path, as we mentioned. And the results I'm going to show it in a few slides, so bear with me. And now let's see how the deep learning model is working. So the idea behind deep learning is the model will extract the features for you. So you don't need to do all the hard work of feature engineering. And we thought that's, okay, so understand that the scripts, the classification task, can be really easy for a human to make, like not that really good, but a human eye can distinguish between obfuscated and non-obfuscated scripts. So we said, why not using a vision model that can do, that is good on vision, and to apply it over our NLP task. So we end up using 1D CNN, 1D convolution neural network, and it was utilizing over the character levels of the scripts. We used only ASCII characters, and the rest were padding with zeros. And the input for the model was the first 2,000 characters of each script. That's it. And the architecture is as follows. So we passed the scripts through various kernel sizes, followed by max pooling, some concatenation, dropout, and finally a linear classifier. The idea was inspired by Zheng et al., 2015. So at this point, we had two good results. I will show the results, okay? Don't worry. We had, for one hand, as I said, the classical approach, the other hand, the deep learning approach. However, we still had some problems with obfuscators that didn't really capture well, the model didn't generalize well on them. And then we decided that we need to do some kind of paradigm shift. And in the paradigm shift, we call it like the generalization path. How we can now do these things even better, because now it's the money time. Okay, so to do so, we use some new technique that's called invariant risk minimization, or IRM in short. The IRM loss is phrased as follows. I'm not going to go through it, don't worry, but the entire idea of this loss is phrasing the experiment a bit different. A bit different in that way that we now lock each obfuscator in a different, on the training set. Each obfuscator is now locked in a separate environment, and the model is need simultaneously get a low error or high score on each of the environments while choosing the same features. By panelizing this term of panelization, by panelizing the model to choose the same features, we hope that in the test set, we will have a generalized enough model to achieve the goal we want. Okay, so now for the results, as I promised.
Thank you, Noy. The IRM approach was inspired by Arbitman et al. We used their article as a basis. And for the results, so for the basic goal, as we mentioned, we actually managed to reach quite good results quite quickly using a logistic regression model. And just to remind you, here we basically just use data from one obfuscator, split it into train and test. And we can see that the F1 score in all 4 of these experiments is over 98. With the advanced goal, things look a bit different. We can see here a comparison between the 4 different models that we trained. And each of the models has 4 different experiments. Again, as a reminder, for each of these experiments, we trained on 3 obfuscators and tested on the 4th one. So for example, this first orange bar shows an experiment where we trained on these 3 and tested on this orange obfuscator, which was actually our most problematic obfuscator. As you can see, with logistic regression, even with some regularization, this obfuscator did not perform as highly as these 3. These 3 actually achieved a high score, but this one was too different for the model to capture when we didn't include it in the training data. So here we can see what happens once we added the IRM loss to the logistic regression model. These three obfuscators over here suffered a little bit of deterioration in the results. However, the orange one shows a significant jump and improvement in the F1 score, which is exactly what we expected from IRM, which is that there is a balance across the environments and the results overall are more similar to each other. With the CNN model, again, we can see some variety in the initial results without IRM, which is partly due to the fact that, like any neural network model, the model learns what it is given and not necessarily what we want it to learn. So again, it wasn't robust enough, but once we did add the IRM loss, we can see another improvement and overall more similarity between the results. For our bonus goal, as we mentioned before, we trained each of the models on all four of our previous initial obfuscators and tested them on 3 completely unseen obfuscators. So if, even in the advanced goal, we might have had some bias because the manual feature engineering process relied on our analysis of these 4 obfuscators, right? In this case, we never looked at these obfuscated samples of the unseen obfuscators and simply tested the model on them. So here we can see that the logistic regression model, even without IRM and just with some regularization, already has quite a good performance. And this could be due to the fact that it was exposed to more data. It saw a variety of 4 obfuscators in the training. IRM didn't change this very much. However, in the CNN, we can see that it did struggle a lot with one of the obfuscators, and this could be because it didn't receive the handcrafted features that we gave it, but relied only on the patterns of the ASCII characters. However, once we added IRM loss here, we can see again a significant improvement in the results. So we'll just give you a small taste of what this CNN model with IRM loss actually sees. We use the method here called guided backpropagation, which is inspired by Springberg et al. And to remind you, the model actually goes over the script on a character level, character by character. And this guided backpropagation enabled us to highlight for each letter a heat map on how high the gradient, how steep the gradient is for that particular letter, which we can say is the model's excitement level for each of the letters. So what we can see here are 2 scripts from the same source scripts with 2 different obfuscators. And we can notice that the model highlighted in red some of the typical obfuscation patterns. And this, even though it wasn't exposed to, even on a non-specific obfuscator basis. Finally, let's wrap it up and talk about our conclusions. So we saw that 1D CNN models can be very quick and efficient feature extractors without all the manual handcrafting of features. On the other hand, a clever feature engineering can be very powerful and enabled us to reach good results, as we saw specifically on the bonus goal, even with a simple model like logistic regression with some regularization. Adding IRM can improve generalization for both the classical and the deep learning approach significantly. Thank you very much for all of you for listening, and our mentors, IMPERVA, and Y-Data, of course, for enabling the project. Thank you. Any questions?
So the question is, if I have a malicious intent, and I want to use the model to actually extrude the intellectual property from the hidden with the hidden code, would that be possible?
This is not specifically related to obfuscation, but I guess as in any, encryption, decryption, cyber realm, there's always like the race between, right, the good guys and the bad guys. And we saw even in our literature review that there are some out there, some de-obfuscation tools that what they try to do is not even just detect obfuscation, but kind of reverse it. So I guess, yeah, these are being developed, and it's like always a race between that and the obfuscators. Should I bring the... Okay.
First of all, very nice. That's very impressive. The second thing, you used AST, the abstract syntax trees, right? Did you run the programs?
No. The JavaScripts? No.
I'm just thinking out loud. If you did run it, okay, and you have the AST, then you could identify the path that leads to the output, right? Because everything is the same in that path, and there are many other distractions. But in that way, maybe you could have identified what are the distractions.
Just from what, again, our literature review showed is in general in code analysis, there are so-called synchronous and asynchronous methods. So the synchronous methods in general include running the code and finding out how it does it. But there are a lot of like practical reasons to prefer asynchronous analysis because first of all, it's faster, it's safer, you don't need to expose your systems to all kinds of codes that you don't want to run. So that's why we didn't go in that direction. You have something to add?
Maybe in a different angle. That's in the same path that you're talking about. There are many works that follows about it's called control flow and data flow, and this is the exact thing what they do, but you can do it statically, meaning you don't need to run the entire code. You can just analyze the AST. So yeah, there are many literatures that we found using this analysis. Maybe even boosting the tree with, not boosting, like feeding the tree with more entities of control entities and flow entities or entries, and then like adding more features to their models. However, while we tried it, didn't really improve. So then we end up with what we showed.
That's very nice. Thank you.
Thank you.